The James Webb Space Telescope, humankind's most recent inestimable eye, connects across incomprehensible distances, catching light that has traveled for over 13 billion years. Regardless, this light tells us something other than a story of time. It uncovers the evolution of our universe, shaped and extended by its continuous expansion. As we peer back at the most far-off systems, we're essentially seeing an ancient period, getting closer and closer to the commencement of the universe, the Big Bang. The theory of the prehistoric cosmic detonation, a primary story of modern cosmology, makes a strong case that our universe began differently and is limited in age. Yet, from its initiation, this singular and significant beginning has been met with incredulity and challenges to its legitimacy. These challenges continue even in standard cosmology. For a very long time, the universe's origin theory held solid, particularly after the discovery of the cosmic microwave background, CMB, in the 1960s. This foundational radiation, a weak, comprehensive murmur across the universe, aligned flawlessly with predictions of a hot, dense early universe. However, recent observations by the JWST have raised doubts and introduced new concerns regarding the veracity of the Big Bang. Through the astounding clarity of the JWST, NASA's enormous time machine, we've seen clusters of ancient galaxies that are far bigger and more numerous than anticipated. These findings challenge our understanding of the universe's earliest stages. As the telescope peers back to when the first galaxies formed, it offers humankind a remarkable view, one that the Hubble telescope could not fully access. In essence, Hubble was inadequate, lacking the sensitivity to distinguish the incredibly faint, redshifted light of these earliest systems. However, with the JWST's state-of-the-art capabilities, we are now exploring as far back as possible, very close to the beginning of time. As we venture into this unknown domain, we encounter a centuries-old mystery: how did the first galaxies truly form? And does the universe, as we understand it, really have a single, definitive beginning? The earliest universe was a hot, dark space, so dense that light could not travel freely. This implies that no matter how powerful our telescopes are, we cannot see any further back using light alone. However, we are not restricted to light alone. New technological advancements in the detection of gravitational waves from colliding black holes may serve as a new pathway to peer into the universe's early stages, perhaps even into the very phenomenon we call the Big Bang. The foundations of the theory of the universe's origin, and the increasing skepticism around it, trace back to the 1920s and 1930s when astronomers first noticed that distant galaxies appeared to be moving away from us. This discovery, together with Albert Einstein's theory of general relativity, set the stage for the Big Bang model. Einstein's equations predicted that a static universe would be unstable, requiring either contraction or expansion. Observing this expansion suggested that galaxies had probably been much closer together in the distant past, hinting at a violent beginning for the universe. The universe's expansion has significant implications beyond merely pushing things farther apart. The light emitted from these distant galaxies stretches, shifting to longer wavelengths over time. Because wavelength is related to energy, with shorter wavelengths being more energetic, this redshift indicates that the universe has been cooling as it ages. By rewinding this vast expansion, we arrive at a time when everything would have been so hot and dense that neutral atoms couldn't exist, creating a uniform, glowing plasma. This glow was confirmed in 1964 when astronomers Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background, an omnipresent radiation field that faintly echoes the universe's fiery beginning. Yet, as the JWST pushes the limits of cosmic observation, its research highlights features in the early universe that strain the conventional Big Bang narrative. We see massive, luminous galaxies where none should exist, clustering in ways that challenge prior expectations. If the Big Bang theory alone doesn't fully explain these irregularities, could other possibilities be at play? At the core of the Big Bang hypothesis lies a singularity, a point of infinite density and temperature where the known laws of physics break down. This is where existence, time, and space, as we understand them, supposedly began. However, while this concept is compelling, it has limitations. Imagine attempting to describe the entirety of the universe packed into a single, infinitely dense point. Our comprehension reaches a limit at this stage. Despite the fact that many aspects of the Big Bang model have been supported by observations and laboratory experiments, this initial singularity remains a profound mystery. This raises an important question: could the universe have experienced a different kind of beginning? In its quest to understand the cosmos, science has found ways to recreate similar conditions. For example, quark-gluon plasma has been replicated in laboratories, and matter-antimatter interactions have been studied to align with early universe expectations. By analyzing and dissecting the cosmic microwave background's fluctuations, we have built a well-supported picture of the universe's evolution. Yet, significant mysteries remain. If all regions of space were once packed together into a single point, why do we observe such uniformity in the universe's temperature? Conventional models suggest that distant regions of space should exhibit varying temperatures, as they could not have had time to exchange energy or information. Additionally, we might expect to find remnants of high-energy events, such as magnetic monopoles or spatial anomalies, but none have been observed. These discrepancies open the door to alternative possibilities. Either the universe inherently possessed these balanced properties from the start, or some mechanism enforced them. One candidate explanation is cosmic inflation, a rapid expansion theorized to have occurred before the Big Bang itself. On December 7, 1979, physicist Alan Guth proposed this groundbreaking idea. He theorized that the universe existed long before the Big Bang and experienced an incredible growth spurt. This inflationary phase could explain why the universe appears flat, uniform, and isotropic. After inflation, the universe would have transitioned into the hot, dense state associated with the Big Bang, setting the stage for galaxies, stars, and planets to form. Nevertheless, even inflation does not resolve every anomaly. For instance, recent JWST observations have revealed unexpectedly large galaxies from the universe's infancy, suggesting a faster rate of formation than inflation alone can explain. The JWST's incredible capabilities offer humankind an unprecedented window into the cosmos. This $10 billion infrared telescope has captured stunning images of the early universe, unveiling a diverse array of massive, brilliant galaxies that existed when the universe was just a fraction of its current age. Previously, astronomers believed they had a solid understanding of how matter coalesced to form the first stars and galaxies. However, the JWST's discoveries suggest a far more rapid development than anticipated. These revelations have sparked both skepticism and excitement in the scientific community. The implications of the JWST's discovery stretch far beyond mere adjustments to our models. They force us to rethink the very fabric of cosmic history. If galaxies formed much earlier and at a much greater scale than previously thought, what does this mean for our understanding of the universe's infancy? Some researchers suggest that our current models of dark matter and dark energy, the unseen forces thought to govern cosmic structure, may need revision. Others argue that new physics, perhaps even an alternative to the Big Bang, could be required to account for the JWST's findings. One possibility is that our timeline for cosmic evolution is flawed. If the first galaxies emerged sooner than expected, it could indicate that the process of star and galaxy formation was more efficient in the early universe. This could suggest that conditions in the primordial cosmos were different from what we had assumed, possibly involving undiscovered mechanisms that accelerated the birth of structure in space. Another possibility is that the universe did not begin as a singularity at all. Some alternative models propose that the Big Bang was not the absolute beginning but rather a transition from a previous cosmic state. The idea of a bouncing universe, for instance, suggests that our cosmos could be part of an eternal cycle of expansion and contraction, eliminating the need for a singularity. The idea of a multiverse also arises in these discussions. Some cosmologists speculate that our universe might be one of many, each governed by different physical laws. If the properties of our universe, such as the rate of expansion and the balance of forces, seem finely tuned for life and structure, it might be because we happen to exist in a universe where these conditions align by chance, while countless others may have failed to develop into anything recognizable. The JWST's unparalleled ability to peer into the depths of time offers an opportunity to test some of these ideas. If we continue to find galaxies that defy our expectations, we may need to fundamentally rethink not only how our universe evolved but also how it began. Yet, even as we challenge old models, some aspects of the Big Bang theory remain remarkably resilient. The existence of the cosmic microwave background, the observed abundance of light elements like hydrogen and helium, and the overall large-scale structure of the universe still align with a hot, dense beginning. This suggests that while refinements may be necessary, a complete dismissal of the Big Bang is unlikely. As JWST continues its mission, astronomers are eagerly anticipating more surprises. The telescope is set to investigate the atmospheres of exoplanets, search for the first black holes, and probe even deeper into cosmic history. Each new observation could bring us closer to resolving one of the greatest mysteries in science: how did everything begin? The answers may not be simple. They may challenge our most cherished theories and force us to confront the limits of human understanding. But in the pursuit of knowledge, each discovery, whether it upholds or overturns our expectations, brings us closer to uncovering the true nature of the cosmos. And so, as we gaze into the abyss of space and time, we are reminded that the universe is not just a story of matter and energy. It is a story of curiosity, of exploration, and of the relentless quest to understand where we come from and where we are headed. Galaxies that are visible in the first 500 million years of cosmic history defy existing models. The JWST preliminary results suggest that galaxies in this early epoch may be far more massive and numerous than previously thought, possibly housing masses equivalent to today's large galaxies like the Milky Way. This rapid development challenges current cosmological models, which implied that a galaxy of this size wouldn't form until 1 to 2 billion years after the Big Bang. According to Nelson's research, galaxies may develop more vigorously than anticipated, prompting the possibility of new theoretical structures for cosmic evolution. Dark matter, an imperceptible and baffling substance, is thought to make up about 85% of the universe's mass, shaping its large-scale structure. Conventional cosmology proposes that galaxies form inside massive halos of dark matter, which gravitationally draw in regular matter, allowing stars and galaxies to coalesce. Yet, JWST observations challenge this model, as galaxies appear to be forming in ways that test our comprehension of dark matter distribution and existence. Dark energy, a similarly elusive force responsible for the universe's accelerated expansion, further complicates the picture. Some models propose that early dark energy, a brief increase in dark energy density, might have accelerated galaxy formation, possibly aligning with JWST discoveries. However, such changes must fit within the broader framework of the standard cosmological model, which already explains cosmic expansion on large scales. As convincing as the Big Bang hypothesis is, it is not the only explanation for the universe's origins. Several alternative theories have gained attention, each offering intriguing perspectives. The steady-state theory, unlike the Big Bang, this theory proposes an infinite universe with no beginning, where matter continuously appears as galaxies separate. According to this theory, the universe expands, but new matter emerges, maintaining a uniform density. However, it does not account for the cosmic microwave background, CMB, which strongly supports a hot, dense early universe. The mirror universe hypothesis, a more speculative idea, suggests that two universes were born in the Big Bang, one moving forward in time and another in reverse. This twin universe would develop backward, providing a mirror image of our own cosmic history. Though highly speculative, it proposes that the universe could be more complex than previously thought. The simulation hypothesis. This theory raises the possibility that our universe is a simulation created by an advanced civilization. Quantum entanglement and the unique nature of space-time lend theoretical weight to this idea. Despite remaining unprovable, the simulation hypothesis challenges our understanding of fate, reality, and existence. The multiverse hypothesis, a popular alternative, this theory proposes a limitless number of universes, each with its own physical laws. According to this model, changes in dark energy are responsible for multiple Big Bang-like events, creating an immense cosmic landscape. As our universe expands, dark energy creates voids, suggesting a continuous cycle of creation, destruction, and rebirth. Each of these hypotheses offers unique insights into cosmic origins, raising new questions about the nature of space, time, and matter. While the Big Bang remains the prevailing explanation, it has been tested and reshaped by new evidence and perspectives. The JWST, with its unrivaled sensitivity, is poised to unlock even more secrets of the universe. As the telescope continues its spectroscopic mission, upcoming data will enable more accurate measurements of distant galaxies, helping scientists refine their understanding of cosmic evolution. Thanks to JWST, our journey into the universe continues to expand. Its discoveries promise to reshape our understanding of fundamental cosmic processes. One area likely to experience significant updates is the formation and evolution of galaxies. Generally, researchers believe that galaxies formed from small clusters of matter that grew over time, organized by gravity. However, JWST has uncovered evidence of galaxies that appear to have formed significantly earlier than previously believed. These earliest galaxies are not just bigger and more varied than anticipated, they also seem to have developed complex structures in a fraction of the time scholars had envisioned. This raises fascinating questions about the processes driving galaxy formation. While gravity certainly plays a crucial role, the discovery of such massive galaxies in the early universe suggests that other factors may be at work. One hypothesis involves the role of supermassive black holes, which could serve as a central mechanism for galaxy formation. If these black holes formed early in the universe's history, their powerful gravitational pull could have accelerated the rate at which matter in the surrounding area collided, leading to the rapid formation of large galaxies. Additionally, the energy released by these black holes could have triggered bursts of star formation, further speeding up galaxy development. JWST's ability to detect light from the earliest galaxies also offers new insights into the chemical makeup of the universe at various stages of its evolution. Earlier telescopes like Hubble could observe distant galaxies, but their sensitivity was limited when detecting the faint light emitted by early galaxies. With its larger mirror and infrared capabilities, JWST can observe galaxies that existed within the first few 100 million years after the Big Bang. These observations reveal a universe that was much more chemically diverse than previously thought. For example, JWST has identified galaxies that appear to contain metals, elements heavier than hydrogen and helium, much earlier than expected. This suggests that star formation in the early universe may have been more complex, with the first stars enriching their surrounding gas with heavy elements faster than anticipated. Unraveling the early universe with JWST. The James Webb Space Telescope, JWST, is revolutionizing our understanding of cosmic history by revealing galaxies that defy previous models. The telescope's infrared capabilities allow it to peer through cosmic dust and detect faint light from galaxies that formed within the first few 100 million years after the Big Bang. These discoveries challenge existing theories of galaxy formation, dark matter distribution, and even the fundamental timeline of cosmic evolution. One of the most surprising findings is the presence of mature galaxies in the early universe. Previously, scientists believed that the first galaxies would be small, irregularly shaped, and composed mainly of young stars. However, JWST has detected galaxies that are not only massive but also well-structured, resembling modern spiral and elliptical galaxies. This suggests that galaxy formation and evolution occurred much faster than previously thought. The role of supermassive black holes. Another crucial aspect of JWST's findings is the potential role of supermassive black holes in early galaxy formation. These black holes, millions or even billions of times the mass of the Sun, are thought to reside at the centers of galaxies. If supermassive black holes formed much earlier than expected, they could have significantly influenced their host galaxies by accelerating star formation. The intense gravitational pull of these black holes could have funneled gas and dust into the galaxy's core, triggering rapid star formation. Generating powerful outflows, energy released by accreting black holes could have heated surrounding gas, affecting how and where stars formed. Shaping galactic structure. Black holes may have played a key role in organizing early galaxies into the disk and elliptical structures seen today. These findings prompt a re-evaluation of current models of black hole formation. Traditionally, supermassive black holes were thought to grow over billions of years through the gradual accumulation of matter. However, JWST's observations suggest that some black holes may have reached enormous sizes in just a few 100 million years, implying that different growth mechanisms, such as direct collapse black holes, could be at play. Challenging dark matter models. The unexpected structure and mass of these early galaxies also pose questions about the role of dark matter in galaxy formation. Standard cosmological models propose that galaxies form within massive halos of dark matter, which gravitationally attract normal matter, allowing stars and galaxies to coalesce. However, some of the newly observed galaxies appear too massive and too organized to fit this model, suggesting that either dark matter behaved differently in the early universe than it does today. Alternative forces or unknown mechanisms accelerated galaxy formation. Our understanding of dark matter itself needs revision. One possibility is that early dark matter halos were much more efficient at pulling in normal matter, leading to the rapid emergence of large galaxies. Alternatively, some researchers speculate that new physics beyond the standard model of cosmology may be required to explain these anomalies. The chemical fingerprint of the first stars. JWST has also provided crucial insights into the chemical composition of early galaxies, shedding light on the very first stars, known as population 3 stars. These primordial stars, composed only of hydrogen and helium, were thought to be extremely massive and short-lived. When they exploded as supernovae, they enriched the surrounding gas with heavier elements, allowing the formation of later generations of stars and planets. Surprisingly, JWST has detected higher-than-expected levels of heavy elements in some early galaxies, suggesting that star formation and chemical enrichment happened much faster than anticipated. This challenges previous models, which assumed that the first few 100 million years after the Big Bang were dominated by metal-poor, primitive stars. Instead, the presence of metals in these early galaxies implies that multiple generations of stars may have formed in rapid succession, fundamentally altering our understanding of stellar evolution in the young universe. Implications for the Big Bang model and alternative theories. While the Big Bang remains the dominant model for cosmic origins, JWST's discoveries force scientists to refine or reconsider some aspects of it. Alternative theories, such as early dark energy, cyclic universes, and quantum gravity effects, are being explored to explain the anomalies observed in early galaxy formation. Some researchers suggest that an unexpected phase of rapid cosmic evolution, perhaps driven by an unknown force or process, could explain how galaxies matured so quickly. Others propose that our interpretation of redshift, the stretching of light from distant objects, may need adjustments, potentially leading to revisions in our measurement of cosmic distances and timescales. Looking ahead, future JWST observations. As JWST continues its mission, upcoming observations will focus on spectroscopic analysis of early galaxies to determine their precise chemical composition and star formation rates. Investigations into dark matter distribution in the first billion years of the universe. Studies of early supermassive black holes to uncover their origins and growth mechanisms. Probing the reionization era, the period when the first galaxies ionized the universe's neutral hydrogen, shaping the cosmos into its current state. Each new discovery from JWST is rewriting the story of cosmic history, offering a deeper glimpse into the universe's origins and evolution. With every observation, the telescope is not only confirming but also challenging fundamental aspects of modern cosmology, opening the door to new scientific revolutions.